Thanks a lot for the introduction. Of course, you know the resting state EEG, nice close and nice open, is really effective to probe the neurophysiological mechanism underlying regulation of vigilance in healthy subjects and in patients. But we have different options to analyze the resting state EEG data. For example, the first is the use of the electrode reference. We can use common average or ear lobes linked or the rest, the new entry in the field. But of course, we do not know the impact of different choices on the final results. And another point in which we can have different options and we do not have the optimal choice is how to detect and remove artifacts, biological artifacts from the EEG, recorded EEG data. You see in this slide the artifacts due to high movements, so eye blink or muscle activity and so on. We have several good options, but we do not the best one. Also, the typical approach of spectral analysis of EEG data presents several options. Now you see the typical fast Fourier transform, but there are other possibilities and maybe even more reliable than the fast Fourier transform from autoregressive models and others. Another really nice opportunity to understand the neurophysiology of vigilance is the disentangling of periodic and aperiodic spectral EEG components. And we have the possibility to separate these components and to have more reliable analysis of the power density peaks in the spectrum, but also of the aperiodic component. Again, we have different options. There is the very popular spectral parameter from FORF, but other procedures are on the desk and we do not really know what is the best way to separate these components. Also, the functional connectivity from EEG data shows different options. For example, we have different procedure for investigating the linear interdependence of EEG at the sensor and source level, the spectral coherence or phase lag index, synchronization likelihood, and others. And we have ever more possibilities to analyze this interdependence of EEG data at the pace of electrodes or sensors with nonlinear techniques, but we do not really know what are the optimal approaches for this point. We know that both are important, but we have several options for linear and nonlinear techniques. Even in the source analysis, we have the same problem. We do not have a unique solution for the source mapping at the cortical level from EEG data. And so we rely on assumptions and implementations of different a priori information and so on. But we really do not know on real data, on recorded data, the best ones. So we can rely on simulated data, but they could not fit entirely the realistic physiological recording situations. For this reason, we discuss within the cost action EEG101 and other communities of G experts the optimal procedure for EEG standards, an international initiative collecting the contribution of different organizations that you see in the slide. The aims is to define a framework, a methodological framework to compare alternative EEG techniques. The idea is to tap over time and compare over time performances of different techniques for artifact detection and removal, re-referencing strategies, and the composition of periodic and periodic spectral components, and the estimation of source activity and connectivity, and even the best machine learning tools to harmonize EEG data collected from different centers. The expected outcomes is that we have some consensus among experts about the optimal procedures to analyze resting state EEG data in the different steps that I mentioned. And also to probably manage the actual barrier for the use of EEG biomarkers in clinical applications that regulatory agency often claim that you have different results with different techniques from the same data. The platform could be based on data, and this data could be in the original proposal 100 resting state eyes closed EEG datasets in healthy subjects from 20 years old to 80 years old, so not affected by brain diseases already diagnosed and so on. And with the idea to have also these 100 data sets recorded with a minimum of 64 scalp electrodes in order also to tap different electrode density to obtain reliable results. The new concept is that the criteria to establish the validity of the performance of each technique. And in the proposal, OPES would like to use two criteria. One is the relationship between the alpha power density at the sensor and source level and the sex. We know from the literature that healthy females, show higher power density in alpha frequencies in the posterior scalp regions or cortical sources. And so you see here a milestone result from the group of Robert Berry showing this difference at the mean level of the group level, but this was replicated by other groups. So the idea is that if you have a good option with your EEG technique to remove artifacts, to compute the spectrum, the power density spectrum, if you are able to disentangle a periodic and periodic, you can obtain a very clear difference in the power density in the alpha frequency between females and males of the 100 datasets. The second criterion for testing validity of each EEG technique is the relationship between alpha power density in resting state eyes closed and age. Again, we have a lot of replications of the results that there are differences in the power density in the posterior areas between younger people and older people in healthy subjects. You see here a milestone result from the group of Robert Berry, and I also plotted some data from the PD Waves consortium And you see that typically you have a greater posterior alpha power density in younger people compared to older people. So ideally, if you have a valid high performance technique to remove artifacts, to compute the power density spectrum, and to disentangle aperiodic and periodic components of the spectrum, ideally you could increase this kind of association between alpha power density and age in healthy subjects. And this can be a criterion to compare different techniques to provide the power density, or to remove artifacts, or to disentangle aperiodic and periodic components. Finally, we discussed the possibility to collect information from the EEG community about the preference in the use of EEG techniques and platforms in the different steps of resting state EEG analysis. And so we discussed with the board of the cost action EEG101 a survey to be proposed to EEG community from the cost action, but also Global Brain Consortium, or EEG Many Labs, and other communities. This survey to know the preference, what the tools that people use, the most popular for the different steps of the analysis. And so ideally, we will launch this survey in a short period. So thanks for your attention.